Okay, friends, if you're here, you're up for a bit of a journey of discovery as to what the hell that is, where it comes from. I mentioned at least once or twice in previous videos, it's always a pain in the ass to not know where formulas come from in math. I think a lot of students get turned off mathematics, to mathematics because they view it as nothing more than a bunch of formulas that they have to plug numbers into, and they have no understanding of what the hell's actually going on. So this video is going to be a bit involved. That's why it's optional. It's going to have some algebra in it. It's going to have some, it's going to have some review from the course in it. This is going to go all the way back to week 2, really. It's going to wrap up everything from week 2 to week 5, kind of in one place. So if you're not a fan of that kind of stuff, you can just turn the video off right now and just go and do the homework. Because you don't need this video to do the homework. You need that formula, but you don't need the explanation of that formula. But if you're up for it, stick with me and we'll take a look right now. Okay. Now, margin of error, going back to last week, the definition, the introduction of confidence. Margin of error is equal to a confidence multiplier times standard error. Well, this is the confidence multiplier, right? That means that thing is the standard error. So if we take that away, we remove margin of and simply call it standard error. Yes! Very good. That was kind of one of the main things we learned last week. When did we learn about standard error? Well, we got to go back one more week for that, to the central limit theorem. The idea that when you sample from a distribution, you end up getting bell curves, which is totally cool. Now, that thing is a standard error. But from week 4, we also know that the standard error is equal to, now bear with me here, it's going to be a little bit wordy, but it needs to be. The standard error is equal to the standard deviation in the sampling distribution for p hat divided by the square root of the sample size. This was one of the coolest results from the central limit theorem. You may have wondered a couple weeks ago why I was using sample sizes of 4 and 9 and 16 and 25. If you remember, it's because those numbers are perfect squares. So when you take the square root of a perfect square, you get a nice number. So that square root of n is one of the coolest results, in my humble opinion, in statistics. But you see that square root of n? That square root of n is also up there. It might not be inherently obvious as to where it is, but you see the big square root over the whole thing? Algebraically, here comes our first little algebra move. Algebraically, we can split that square root across both pieces. That's a function in algebra you could do, or a property in algebra you could do. Ha-ha! This tells us a number of things. Standard error, standard error. Square root of n, square root of n. That tells us that the standard deviation of our sampling statistic must be equal to this thing right here. And that, my dear friends, is going to bring us back a week before the central limit theorem. Standard deviation. How do you construct standard deviation? Well, we only did it one time, and I swore I would never have you do it again. So, again, this is a completely optional video. If you don't want to see it constructed again, you don't have to watch this. But I am going to do it to make sure that you understand where that margin of error comes from. Okay. Now, when you're doing a study on a proportion, what you're really doing is counting. You have a sample of a certain size, and then you're going through the sample one by one, and you're keeping track of whether or not the member of your sample has a certain characteristic you're looking for. Presence or absence of a disease, presence or absence of a gene, presence or absence of a yes vote. I mean, the possibilities are basically limitless. One of the ones we did today, presence or absence of a head when you spit a coin. One way of thinking about that is, in the outcomes of each one of those trials in the experiment, register a 1 if it's got what you're looking for, and register a 0 if it doesn't. Binomial. Call it a 1 and add 1 if it's got what you're looking for. Don't add anything. Add 0 if it doesn't. Easy peasy lemon squeezy. Not a problem at all. Now, each of those outcomes has a probability. based on your study. And you already know what the answer is. The probability of the presence of the variable is going to be p hat. That's what you get from the study. You get p hat from that study. 0, this is a little bit trickier. For years and years and years, this was called q hat. I'm going to write that down real quick and then erase it. It was called q hat because the formula looked nicer at the end. But I don't like calling it q hat because q hat makes it seem like it's not related to p hat at all. But it is. Let's throw some numbers in. Let's say p hat is 0.5. That means this thing happens 50% of the time. Well, that means it doesn't happen 50% of the time. That makes perfect sense. Let's say p hat is something like 75% of the time. Well, that means this thing here has to be 25% of the time. Hopefully you're seeing that if you add these probabilities together, they add up to 1 every time. They have to. It either happens or it doesn't. 100% of the time. So that means to find this remaining piece, it's 1 minus whatever that one is. That should make sense. It's a little bit algebraic, but it's also general, which is why we like algebra. It's arithmetic, but generalized arithmetic. Okay, good. Now, the next thing we have to do, this is called a probability distribution. You don't have to, this is one of those things I spent a lot of time in the old 243 doing, a whole week on the probability distributions, and I loved it so much. And unfortunately, it had to get yarded out. And anyway, I'm not going to complain too much about the state of Oregon and what they did to my beautiful stats course. It's still a beautiful stats course. It's just a little bit fast for my liking. Anyway, we got to calculate the standard deviation. If you think back to week 3, now we're back to week 3 now. Standard deviation is defined to be the average distance of each of the data points from the average. Average distance from average. Okay. The average of this distribution is p hat. That's the definition of what a proportion is. A proportion is an average. It's an average rate, p hat. So, the outcome minus the average for each of these, 1 minus p hat is just 1 minus p hat. 0 minus p hat is just 0 minus p hat. You're just taking each data point and subtracting the average from it. This will be greater than average. This will be less than average. That's why it's negative. Okay. Again, algebraic. It's easy to get lost in the algebra, but we're going to break it, kind of go a little bit slow at a time here. Now, the next part that you may have forgotten about in week 3. I just told 2. Week 3. The next thing we had to do was square those differences. So we're going to take those outcomes and square the differences. Now I'm not going to multiply them out. I'm just going to write them as 1 minus p hat, the quantity squared, and 0 minus p hat, I guess, the quantity squared. Just going to write it like that, multiply by itself. The reason we did that was to remove negatives so that the overall sum was going to be positive. Now here's the one thing we never did in this class, only because there's no time. We have to weight these results because they don't happen uniformly. In a normal data set where every data point happens with the same frequency, you can just add these things up and call it good. But these don't happen with the same frequency. This one happens that often and this one happens that often. So we have to do one more column, which is the outcome minus that p hat squared times the probability. It's a weighted standard deviation, if you will. So it's going to be, I'm going to leave it in algebraic phrasings. This, 1 minus p hat squared, times p hat. This one is 0 minus p hat squared, times 1 minus p hat. Okay. Now, remember, I'm going to put this in the back of your mind right now. Remember when we squared right here? We're going to have to take a square root at the end of this to get rid of that squared. That's why that square root was in the margin of error calculation. We have to undo the squaring we did here, just like we did with standard deviation back in the day. Okay. The first thing we have to do is add those two things together. So right now, this thing, it has a name. I think I probably mentioned it back in week 3. It's called the variance. When everything is still squared, the measure you're looking at is called the variance. So the variance is those things added together. 1 minus p hat squared times p hat plus 0 minus p hat squared times 1 minus p hat. Okay, that's the variance. Now, when we get done, we have to take the square root of this thing, and that becomes the standard deviation. That's by definition, that's what it is. Okay. Now, I can't help but notice a couple things. First, see this plus sign right here? My algebra brain is tickling now because that means I've got this plus this, and my algebra brain is saying, look for common factors. Look for common factors. The first thing I notice is there's a 1 minus p hat here, and there's also a 1 minus p hat here. And that makes me kind of happy. I'm pretty stoked about that, actually. I also notice that there's a p here. There's a negative p here, but, negative p there. But if I was to simplify this, 0 minus p hat is just negative p hat. If I square that, that's going to become a positive p hat. That was the whole point of doing that, right? So I'm going to do something here. Plus, this is going to be p hat squared times 1 minus p hat. Now I like this algebraically because now, check this out. I can pull one of these 1 minus p's out and pull that 1 minus p out. And I can also pull this p hat out and one of these p hats out. And what gets left behind, I left behind this 1 minus p hat here. And I left behind that 1 p hat there. And now what is really cool, leave this alone. That should look familiar to you. Yes. This is 1 minus p hat plus p hat. Well, those are the same number, but one's negative. That means they cancel. And that's just times 1. So really, if you think about it, this whole thing just equals 1, which means it doesn't really equal anything of interest other than 1, which means the only part of it that's interesting is this. Well, that should look like what used to be written up there in that top right corner, making me wish I had bigger chalkboards. It was written the other way around, with the p hat in the front and the 1 minus p hat in the back. But that doesn't matter. Those two things are equal to each other. Friends, we now know the variance is p hat times 1 minus p hat, which means the standard deviation of this distribution is just the square root of that. Which is what we were trying to show in the first place. That's why the formula makes sense. Because algebraically, you can show that if you calculate the standard deviation of the distribution of the results in a proportion study, you end up with that standard deviation. Then you take that standard deviation, divide it by the square root of n, you get the standard error, and then you multiply it by whatever confidence multiplier you need to get the margin of error that you need. I don't know about you, I feel better after seeing that. All right, my friends, take care of yourselves. We'll see you next time.